Hi, I'm James Ford. I'm a senior technical product manager with Unity Technologies in our AI organization. And I'm happy to talk to you today about how to supercharge your computer vision applications with synthetic data from Unity. So let's dive in. So computer vision is becoming essential in retail. And in our conversations with customers that we work with, we see applications that range from things like planogram verification, where you essentially have a digital representation of where objects are supposed to be on the shelf or in different kiosks in stores, and then using computer vision to verify that the objects are actually in those locations or at certain stock quantities in those locations, basically checking that what is in the store matches what was digitally planned. We also see applications around the shopper journey, where it's important for a retailer to understand how individuals are traversing a physical store and to be able to optimize item placement for maximum exposure or just other types of analytics around shoppers within the store. We also see applications of cashierless checkout, where it's really important to understand how shoppers are interacting physically with items in a store to know whether or not they've basically chosen them and are going to check out with those items. And that is a complex computer vision task that involves the interaction of basically two entities, a moving human with certain poses and different objects that are classified within a store. And then another one is just inventory monitoring. And we're seeing cases where companies are using robotic solutions and just smart cameras to make sure that the stock in the store isn't running out. So things like out of stock notices. This is just a broad summary of the types of things that we are speaking with our customers about. And it certainly goes deeper than this. I just wanted to start with an overview here. And even in the coming roundtable discussion, would love to hear about additional use cases that you all may be seeing on your side. So a key to all of these computer vision applications is to build, typically these days, a machine learned model for doing the computer vision recognition. And a machine learned model, typically we use deep learning and high volume labeled data is a key to a performant and efficient computer vision model. So data is the key to computer vision, and that's really what this talk is about today. And I'm going to dive into some of the details around data sets and what it takes to create a performant data set. So let's walk through the computer vision workflow as it has been traditionally understood and talk about some of the challenges in this expensive process. Step one is typically the acquisition of real-world images. And by this, I mean, maybe there are already cameras in the retail environment and there's the acquisition of footage, which is one method of acquiring data. Or let's say that infrastructure is in place. Maybe companies are hiring external contractors to collect representative real-world images. And then once those images are collected, there's often another firm that does the labeling and annotation of those images, basically drawing things like bounding boxes and semantic segmentation to prepare the images as they need to be prepared with metadata for machine learning. And once that expensive 2 steps is completed, which can oftentimes take a month, then you pass the data off to a team that's preparing a computer vision model, and they do extra preparation of the data. They're training a model, they're trying different model architecture, and once the CV model is trained, it is then evaluated for performance against the criteria. Is this thing actually ready for the application? And then finally, if it meets the criteria, then you can go about deploying the CV model into some kind of inference architecture to essentially have it perform in the real world, whether that be in the smart camera, on some kind of robotic device, in an AR application, etc. the applications are diverse. So this looks rather linear, but almost always the first version doesn't work, and there's an iterative loop where you can either iterate on the model with the same data, which can help in certain cases, or you may have to go back to the well to acquire more real-world images and then label and annotate them again. Again, passing the process off to multiple owners and incurring these expenses in terms of both cycle time, again, up to a month per cycle, and the actual dollar cost of each of these. And that could mean that actually getting a model to deployment could take something like 3 months, 6 months, a year, more than a year. That's not unheard of in the conversations that we've been having. So I really want to hone in on the idea that in this whole cycle, we have data that 70% of the time spent on the collection, labeling, and annotation, it's really in these two steps. And this is where we've been focusing a lot of our attention in the AI organization at Unity. And I just want to now draw a comparison between what we just described, the real-world data problem, where we're typically dealing with thousands of hand-collected images, getting teams like you see above to annotate these images. Again, the annotation itself being done by humans is manually prone to error, and more people are creating solutions to try to automate the annotation, but ultimately in the end, it is still an error-prone process with real-world images. It's biased to what is available, meaning let's say you have different lighting conditions in an outdoor kiosk, and you want a computer vision model to be able to detect the stock. You're only going to be able to create a computer vision model that's performant for the data, the lighting conditions from which you've collected the data. So let's say you have a low lighting condition. Now all of a sudden your model may not perform well if you don't have data for that lighting condition. And then lastly, sometimes it's not privacy compliant, meaning that if there are people that are in those images, now, especially nowadays, companies are very particular about ensuring the privacy of their customers. And there are also government regulations around this that are becoming increasingly prevalent. So there are issues where people can't use the data they would like to use for training. Now let's talk about, in comparison to real-world data, the idea of synthetic data. And this is really the solution that I want to hone in on over the course of this talk, is that synthetic data is a means of computer generating data, typically from some underlying 3D content, and I'll dig into 3D content in depth, where you can generate millions of images. There's some upfront cost in creating the underlying 3D content, but then very little incremental cost in creating huge data sets that cover a large variety of use cases. The data as it's generated is automatically and perfectly annotated because you build code into the data generation that does the annotation and understands the underlying objects. It means you don't have to have a separate team doing this annotation process. It's automatically annotated. It's randomized for unbiased performance, and I'll talk about what randomization means. And if it's done right, it's 100% privacy compliant. It avoids these privacy issues. So let's talk about domain randomization. Domain randomization says if you vary features of your data set that you don't want the model to be sensitive to, like lighting, you can create a data set, you can create a model by training with that data set that is very robust across those conditions. And oftentimes, you can create data sets that don't even look like the thing in the real world. You can see how random these data sets really look, and they do help model performance. This is just a start. So let's look at some problems that we actually tackled with this approach. With real-world data only, you can see that this grocery object detection problem didn't perform well, especially under complex configurations and low lighting conditions. But with synthetic data, where we've varied the lighting, you can see just by the virtue of the green boxes on the bottom that the performance of the model increased substantially in these what I'll call edge cases. So think about all the edge cases your computer vision application might encounter, and if you create data sets that cover those edge cases, now all of a sudden you can get a highly performant model in those conditions. So this is just an experiment, and then I'll go on to show that our customer and partner NeuralPocket we just released a blog post with them on this particular application, used the same approach to train a smartphone detector for one of their applications. And you can see the highly randomized data set almost looks like nonsense, except for the fact that you can recognize hands and smartphones in the data set. They were able to reduce costs for their data collection and annotation by 95%. They're able to reduce the total model development life cycle when compared to using just real world data by 95%. And in the end, they improved their computer vision model performance. And I'll just go on to show a second example. Imagine security use cases inside of a store. Here we have a knife, gun, and bat detector detecting dangerous objects. And you can see the performance, the accuracy of the model when just using real world data. We get massive boosts when synthetic data is applied to these data sets. All right, so now I want to dig a little bit deeper into the idea of 3D content. We talked about randomized data sets, and really Unity is where 3D assets and environments for synthetic data come together. So I'll talk a little bit about assets to start with. High quality 3D assets can be key to a synthetic data set. And internal teams in Unity have spent a lot of effort creating scanning solutions for high quality 3D assets. And we've built a lot of skill around technical artistry for developing high quality 3D assets. Those were just some examples. We also have been developing pretty deep technologies for creating structured and randomized environments. Some computer vision problems may do well with the totally randomized approach that I showed, and some may require more structured environments like these. This is a home, but you can equally imagine a store shelf being structured and randomized to account for different conditions. So bringing those things together, you can imagine that data sets can be quite structured and varied. Another thing that I want to talk about, we mentioned cashierless checkout as one example of this, is that it's one thing to have objects in an environment. When humans come into play, that adds another element of complexity into data set generation. And we have tools that enable the annotation of human models for pose estimation such that they can be incorporated into models that get trained. So I think the last thing that I want to show is that we have a retail data set for download. And this data set employs a number of different objects that we've scanned, and we have annotated these. And we make this data set available to you for your experimentation, and we'd love to get your feedback on the usage of this data set. And so I'll just wrap up by, again, drawing the comparison here. Real world data has traditionally been used for computer vision applications. It's expensive to collect real world data. It takes a lot of time, and these things add up to the lengthening of the overall life cycle of developing a computer vision model. Real world data is often biased and insufficient, and there are privacy and compliance issues associated with real world data. And I'd like you to think about Unity computer vision for your synthetic data needs. Please contact us and request a sample data set today. Here's a link for contacting us, and again, we can provide you with that retail data set, and we'd love to hear about your computer vision needs. And that's it for my presentation.